Hello, in this lecture we'll find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. We start with the first method and we join points P and B together by a straight line. And I'll copy the white semicircle in a new page and we will implement rule 7 on this white semicircle. So actually, this is the white semicircle with a copy from the original drawing. AB, side AB is the diameter of this white semicircle. So I'll write it down. By joining points P and B together by a straight line, we created the peripheral angle APB. This is peripheral angle APB, and it is subtended on AB. It is the diameter of this semicircle. So now we can implement here rule 7. I will repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equals to 90 degrees in its size. So in the drawing we have a circle, line segment AB is the diameter of this circle, and we have also here peripheral angle ACB. This is peripheral angle ACB. It is subtended on AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral angle ACB equals to 90 degrees in its size. Okay? So whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So I can actually implement rule 7 in our drawing. Why? Because in our drawing we have, this is peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Likewise, we join points P and C together by a straight line. and I'll copy the green semicircle in a new page, and we'll implement rule 7 on this green semicircle. So actually, this is the green semicircle that I copied from the original drawing. AP is of course the diameter of this green semicircle, so I'll write it down. AP is the diameter of this green semicircle. Actually, by joining points P and C together by a straight line, we created the peripheral angle PCA. This is peripheral angle PCA. Peripheral angle PCA is subtended on PA, that is the diameter of this green semicircle, and therefore according to rule 7, peripheral angle PCA must be equal to 90 degrees in its size. This is angle A. Angle A is a common angle. That belongs both to the green triangle APC, and this common angle A also belongs to the right triangle APB. So angle A is a common angle that belongs to both triangles. So we define the size of this common angle, angle A, as alpha. Actually, this is the common angle, angle A, that is equal to alpha according to our definition. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees, Therefore, this missing third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, this right triangle ACP, this is the common angle, angle A. This is equal to alpha according to our definition. This angle equals to 90 degrees according to rule 7, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that this green right triangle APC is similar to this white right triangle, triangle APB, according to angle similarity rule. So I'll copy those two right triangles in a new page, and we prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB in the right triangle APB. And it is equals to this angle, that is actually angle PCA in the green triangle APC. Repeat again. Angle APB in the right triangle equals to angle PCA in the right triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle. It belongs to both triangles. We have angle alpha here in the right triangle. So I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha as it is belongs to this right triangle, it will be defined as angle PAB. And it equals to itself. So if we define angle alpha as it belongs to this green triangle, it will be defined as angle PAC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle PBA in the right triangle. And it is equal to this angle, that is actually angle APC in the green triangle. So I repeat again, angle PBA in the white triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles in this green triangle APC are correspondingly equal to all the triangles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle, the right triangle APB is similar. This is the sign of similar to the green triangle APC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AB in this right triangle over side AP in this green triangle equals to side AP in this white triangle over side AC in this green triangle. Repeat again. We will derive that side AB in the right triangle or side AP in the green triangle equals to side AP in the white triangle or side AC in the green triangle. What is the length of AC? What is the length of AB? AB in total equals to 5 plus 1, that is 6. So we substitute AB by 6. This equation, it is 6 over AP. That is equals to AP. AP is the missing side, so we leave it as it is. Over AC. What is the length of AC? AC equals to 5 units in its length, according to what is given as the question. So we substitute AC in this equation by 5, and we get that 6 over AP equals to AP over 5. Here we cross multiply this equation, and we get that 5 times 6 is 30. So 30 equals to AP times AP, that's AP square. So AP square equals to 30. We take a root out of this equation, and finally we get that the missing sign AP equals to the square root of 30 units in its length. This is the missing sign AP, and it is equals to the square root of 30 units in its length. AP is actually the diameter of this green semicircle, so I write it down. Here AP equals to the square root of 30 units in its length. So the diameter AP of this green semicircle equals to square root of 30. So the radius of this green semicircle, the radius R, must be equal to the diameter over 2. That is to say, it must be equal to the diameter AP over 2. So I write it down. So the radius R of this green semicircle must be equal to the diameter AP over 2. The diameter AP is square root of 30, and square root of 30 over 2 is the radius of this green semicircle. So if we found out that the radius of this green semicircle R equals to the square root of 30 over 2 units, our mission is to find out the area of this green semicircle. The area of this green semicircle equals to the area of the circle that is pi r square over 2. So I write it down. The area of the green semicircle of this green semicircle equals to pi r square over 2. So it is pi. We just right now found out that r equals to the square root of 30 over 2. Therefore r square must be equal to the square root of 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi. And here we have square root of 30 square is 30, over 2 square is 4, divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2 is 30 over 4 times 2. So the value of this expression in total, we have here 30 over 2 is 15. Therefore in total the value of this expression is 15 pi over 4. 15 over 4 is 3.75. So in total the value of this expression is 3.75 pi, and 3.75 pi is equals to 11.78. In conclusion, I should found out that the area of the green semicircle equals to either 3.75 pi square units, or in terms of numbers, this equals to 11.78 square units. repeat again. Actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, this equals to 11.78 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we will join points P and B together by a straight line. And I'll copy this white semicircle in a new page, and we will implement rule 7 on this white semicircle exactly as we did in the first method. So actually, this is the white semicircle that I call it from the original drawing. Again, AB is of course the diameter of this white semicircle, so I'll write it down. Actually, by joining points P and B together by a straight line, we created here peripheral angle APB. This is peripheral angle APB, and peripheral angle APB is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. So this is a right angle. Peripheral angle APB equals to 90 degrees in its size. So here, this is peripheral angle APB. This is peripheral angle APB, and it is a right angle according to rule 7. And because of the fact that peripheral angle APB is a right angle, it means that line segment BP is perpendicular to line segment PA. Again, line segment BP is perpendicular to line segment PA. But what is PA? PA is the diameter of this green semicircle. So line segment BP is perpendicular to the diameter PA of this green semicircle. And we know that the center of any circle or semicircle always passes through the diameter of the circle. Therefore, the center of this green semicircle must be somewhere between points P and A, because PA is the diameter of this green semicircle. So This is point O. Point O is the diameter of this green semicircle. Point O is the center of this green semicircle because of the fact that it is located on the diameter PA. It is in the middle of the diameter PA. So point O is the center of this green semicircle. Point P is the point of this green semicircle itself. Therefore, PO is the radius of this green semicircle. We define the radius of this green semicircle as R. Therefore, PO equals to R. So in conclusion, we can say that line segment BP is perpendicular to the radius PA, and therefore line segment BP must be also perpendicular to PO, that is the radius of this green semicircle. Why? Because of the fact that PO is part of PA and BP is perpendicular to PA, BP must be also perpendicular to PO that is part of PA. Because if a straight line is perpendicular to another straight line, then the straight line must be also perpendicular to the part of the straight line. PO is part of PA, and therefore we know that BP is perpendicular to PA, therefore BP must be also perpendicular to the part of PA that is PO. In conclusion, you can write down that line segment BP is perpendicular to the radius PO of this green semicircle. And therefore, we can implement a rule 1. Whenever you have a line segment that is perpendicular to the radius of a circle, you can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the domain we have a circle, and OM is the radius R of this circle, and according to this rule 1, line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO. And because of the fact that line segment AB is perpendicular to the radius MO, line segment AB is defined as a tangent to this circle at point M. Again, line segment AB is defined as a tangent to this circle at point M. So whenever, according to rule 1, whenever you have a line segment that is perpendicular to the radius, then that line segment, actually it is perpendicular to that radius at its endpoint, that is point M, and therefore line segment AB is defined as a tangent to this circle. Actually, line segment AB is a tangent to this circle at point M. So we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO of this green semicircle, and therefore according to rule 1, line segment BP must be defined as a tangent to this green circle. So I write it down. This is line segment BP, and according to rule 1, line segment BP is a tangent to this green semicircle. Line segment BP is a tangent to the green semicircle. Actually, line segment BP is tangent to this green semicircle at point P. Okay, point P is the point of tendency of tangent BP with this green circle. So from the common extreme point B, we have tangent BP to this green semicircle, and for the same common extreme point B, if we draw a straight line towards this green semicircle, it will cut this green semicircle at 2 points, C and A. In this way, chord CA will be created. In conclusion, you can say that from this common extreme point B, we have tangent BP, and also we have chord CA. And therefore, we can implement here rule 10. I'll repeat quickly on rule 10. rule 10 is true in any circle. So in any circle, if AB is any chord, we have here chord AB, and PT is a tangent to the circle. Here PT is a tangent to the circle point T. So for the current sum point P, we have tangent AB, and we have tangent PT and chord AB. So in this drawing, the following equation will be true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, we have, if we focus on this current sum point B, from this current sum point B, we have tangent BP to this green semicircle, and from the same current sum point B, if we draw a straight line towards this green semicircle, it will cut this green semicircle at 2 points C and A. In this way, we can derive chord CA. Therefore, all the requirements of rule 10 are satisfied, and therefore, according to rule 10, the following equation will be true, that BP square equals to BC times BA. Again, BP square equals to BC times BA. So I write it down. BP square equals to BC times BA. Repeat again. If we focus on the current sum point B, then the following equation will be true. BP square equals to BC times BA, according to rule 10. BP is the missing tangent, so we'll leave it as it is. BP square equals to BC. BC is 1, therefore we substitute BC the equation by 1 times BA. BA in total equals to 5 plus 1, that is 6. Again, BA equals to 5 plus 1, that is 6. So we substitute BA in the equation by 6. In conclusion, if we found out that according to rule 10, BP square equals to 1 times 6, that is 6. So BP square equals to 6. We take a root out of this equation, and finally we found out that the missing tangent BP is equals to the square root of 6 units in its length. So this is the missing tangent PB, that is equals to the square root of 6 units in its length. So I write it down. In the next step, I'll copy the right triangle APB in the new page, and we will implement the Pythagoras theorem on this right triangle APB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB equals to 5 plus 1, that is 6. And PB equals to the square root of 6. AP is the only missing side that we have to find. We find out the value of AP according to the Pythagoras theorem. So actually, this is the right triangle APB that according from the original drawing. According to the Pythagoras theorem, in this right triangle APB, AB squared, that is the square of the hypotenuse, must be equal to AP squared plus PB squared. And AB squared equals to AP squared plus PB squared. So I write it down. AB squared, that is the square of the hypotenuse, must be equal to AP squared plus PB squared. The hypotenuse AB equals to 6, therefore AB squared is 6 squared, that is 36. And it is equals to AP squared. AP is the missing side, so we leave it as it is. Plus PB squared. PB is square root of 6, therefore PB squared is square root of 6 squared, that is 6. So in conclusion, we found out that 36 equals to AP squared plus 6. Here we subtract 6 from this equation, and finally we get that AP squared equals to 36 minus 6 is 30. Here we take out of this equation, and finally we get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP that equals to the square root of 30 units in its length. Our mission is to find out the area of this green semicircle. And the area of the green semicircle equals to pi r squared over 2. So write it down. Repeat again, the area of this green semicircle equals to pi r squared over 2. We actually found out that the diameter AP of this green semicircle equals to the square root of 30, and therefore the radius must be equal to half of it. The radius r of this green semicircle must be equal to the diameter AP over 2. The diameter AP is square root of 30, so square root of 30 over 2 is the radius of this green semicircle. So r, this is the radius of this green semicircle, equals to the square root of 30 over 2. And the area of the green semicircle equals to pi r squared over 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So in total, the area of the green semicircle equals to pi square root of 30 squared is 30 over 2 squared is 4 divided by 2. So in total, the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So what is the value of this expression? We have here 30 over 2 is 15. So in total, the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75. And in total, the value of this expression equals to 3.75 pi. And 3.75 pi is 11.78. So in conclusion, we shall find out that the area of the green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Repeat again. Actually, in both methods, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. We finished with the second method. In the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So, in the drawing, we have two semicircles. Line segment AC equals to 5 units in its length, line segment CB equals to 1 unit. And our mission is to find out the area of this green semicircle. So, in the first method, we join points P and B together by a straight line. And then I copied this white semicircle in a new page and implemented rule 7 on this white semicircle. So actually, this is the white semicircle that I copied from the original drawing. AB is of course the diameter of this white semicircle. AB is the diameter of the white semicircle. By joining points P and B together by a straight line, we create a peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle, and therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Why? Because according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this is peripheral angle APB that is subtended on the diameter AB of this white semicircle. Therefore, peripheral angle APB is a right angle. Okay. In the next step, we join points P and C together by a straight line, and I copied this green semicircle in a new page, and we implemented rule 7 on this white and this green semicircle. Okay, this is the green semicircle that I copied from the original drawing. Again, AP is the diameter of this green semicircle, and by joining points P and C together by a straight line, we created a peripheral angle ACP. This is peripheral angle ACP. Peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle, and therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. Okay. In the next step, I copied this green right triangle APC and this white right triangle APB in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. But before that, if we look on this original drawing, this is angle A, that is a common angle, it belongs to both triangles. Angle A belongs to the green triangle APC, and angle A also belongs to the triangle APB. So angle A is a common angle that belongs to both triangles. So we define the size of this angle A as alpha. You can see here. So this is the common angle A, that is equals to alpha according to our definition. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees according to rule 7, Therefore, this first BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this main right triangle APC, this is the common angle A. This is equal to alpha according to our definition. This angle equals to 90 degrees according to rule 7, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, I copy this green triangle APC and this right triangle APB in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are called for the original drawing. We prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is the common angle, it belongs to both angles. We have angle alpha and this green triangle, also this is angle alpha. So we can write down that angle alpha equals to itself as a common angle that belongs to both angles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the three angles in this right triangle APB are correspondingly equal to all the three angles in this green triangle APC. Therefore, those two right angles are similar to each other according to angle similarity rule. Repeat again. The right triangle APB is similar, this is the sign of similar, to the green triangle APC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, derive that the following relationship exists between their sides. We derive that side AB in this right triangle over side AP in this green triangle equals to side AP in this right triangle over side AC in this green triangle. Repeat again. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. AB in total equals to 5 plus 1, that is 6. So we substitute AB by 6. AC equals to 5. Therefore, we substitute AC by 5. And finally found out actually that 6 over AP equals to AP over 5. We cross multiply this equation and found out actually that 5 times 6, that is 30, equals to AP times AP, that is AP squared. So AP squared equals to 30. We took out of the equation and finally found out that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP, and it is equal to the square root of 30 units in its length. AP is the diameter of this green semicircle. If the diameter AP equals to the square root of 30, the radius must be equal to half of it. That is to say, the radius R of this green semicircle must be equal to the diameter AP over 2. The diameter AP is equal to 30, and square root of 30 over 2 is the radius R. In conclusion, I found out that the radius R of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of the green semicircle must be equal to the area of the circle, that is pi r squared over 2. Repeat again. The area of the green semicircle must be equal to pi r squared over 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So it is pi and square root of 30 squared is 30 over 2 squared is 4 divided by 2. So in total, the area of the green semicircle equals to pi times 30 over 4 over 2. So it is pi and 30 over 4 over 2 is 30 over 4 times 2. So the total of we found out the area of the green semicircle equals to 30 pi over 4 times 2. Here we have 30 over 2 is 15, so in total the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore the value of this expression in total equals to 3.75 pi. 3.75 pi is equals to 11.78. So in conclusion, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers it is equals to 11.78 square units. We finish with the first method. In the next step I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by straight line. Okay, and then I copied the white semicircle in a new plate, and we implemented all 7 on this white semicircle. So actually, this is the white semicircle that I got from the original drawing. AB is of course the diameter of this white semicircle. Here AB is the diameter of the white semicircle. By joining points P and B together by straight line, we created a peripheral APB. Peripheral APB is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral APB must be equal to 90 degrees in its size. Here you can see that peripheral angle APB is the right angle according to rule 7. So here, this is peripheral angle APB, this is equals to 90 degrees according to rule 7. What is the meaning of peripheral angle APB equals to 90 degrees in its size? It means that this 97 BP is perpendicular to PA. Again, 97 BP is perpendicular to PA. So PA is the diameter of this green semicircle. Therefore, 97 BP is perpendicular to the diameter PA of this green semicircle. And the center of this green semicircle is located here at point O. So this is point O is the center of this green semicircle. Point P is the point on the green semicircle itself. Therefore PO is the radius of this green semicircle. In conclusion, you can find out that because of the fact that 97 BP is perpendicular to the diameter PA, 97 BP must be also perpendicular to the radius PO. Okay, why? Because the radius PO is part of the diameter PA. And if 97 BP is perpendicular to the diameter PA, it must be also perpendicular to the radius PO. Because the radius PO is part of the diameter PA. So you can find out that 97 BP is perpendicular to the radius PO of this green semicircle. And whenever you have a line segment that is perpendicular to the radius, you can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius 1 to its point of tendency. So in the drawing we have a circle, and we have OM, line segment OM is the radius of this circle, that is equals to R. And according to this rule 1, line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO. And according to this rule 1, whenever you have a line segment that is perpendicular to the radius, then that line segment must be defined as a tangent to this circle. Okay? Line segment AB is a tangent to this circle at point M. Again, whenever you have a line segment that is perpendicular to the radius, then that line segment must be defined as a tangent to the circle. Naturally, we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO of this green semicircle, and whenever you have a line segment that is perpendicular to the radius, it must be defined as a tangent to the circle. Therefore, line segment BP is a tangent to this green semicircle. Actually, line segment BP is a tangent to this green semicircle at point B. So, from the common exam point B, we have tangent BP to this green semicircle. And from the same common exam point B, if you draw a straight line towards this green semicircle, it will cut the green semicircle at 2 points, point C and point A. In this way, chord CA has been created. So we can say that from the common exam point B, we have line segment tangent BP. That is tangent to this green semicircle at point P, and from the same common exam point B, if we draw a straight line towards this green semicircle, we create chord CA. Okay, and therefore we can implement here rule 10. According to rule 10 is true in any circle, so in any circle, if from the common exam point P, we have here tangent PT, this is tangent to this circle is point T, and from the same common exam point P, if you draw a straight line towards this circle, it will cut the circle at 2 points, point A and point B. In this way, chord AB has been created. So in this drawing, the following equation will be true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement this rule 10 in our drawing. Why? Because in our drawing, if we focus on this common exam point B, from this common exam point B, we have tangent BP, that is tangent to this green semicircle at point P. In addition, from the same common exam point B, we have here, if we draw a straight line towards this green semicircle, it will cut the green semicircle at 2 points C and A. In this way, we create here chord CA. So all the requirements of rule 10 are satisfied, and therefore according to rule 10, the following equation will be true, that BP square equals to BC times BA. Again, BP square equals to BC times BA. Repeat again, according to rule 10, if you focus on the common exam point B, the following equation will be true, that BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is. So BP square equals to BC. BC is 1, so we substitute BC by 1. BA times BA. BA in total equals to 5 plus 1, that is 6. So we substitute BA by 6. Here, we substitute BA by 6 and BC by 1. So in conclusion, we can find out that BP square equals to 1 times 6, that is 6. So BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. So this is the missing tangent BP, that equals to the square root of 6 units in its length. In the next step, I copied this right triangle APB in a new page and implemented the Pythagoras theorem on this right triangle APB. This is the right triangle APB, that according to the original drawing, we just right now found out that line segment PB equals to the square root of 6 units in its length. AB is 5 plus 1, that is 6. The diameter AB is 6. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. The hypotenuse in this right triangle is AB, therefore the square of the hypotenuse is AB square, and AB square must be equal to AP square plus PB square. So again, AB square equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36, and it is equal to AP square. AP is the missing side, so we leave it as it is, plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in conclusion, we actually found out that 36 equals to AP squared plus 6. Here we subtracted 6 from this equation and finally found out that AP squared equals to 36 minus 6 is 30. So AP squared equals to 30. We took out all of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. If the diameter AP equals to square root of 30, it means that the radius must be equal to half of it. The radius of this green semicircle must be equal to half of it. So the radius R of this green semicircle must be equal to the diameter AP over 2. AP is equal to 30 and AP over 2 is equal to 30 over 2. So the radius R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to the area of the circle that is pi r square over 2. Okay, again, the area of this green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So it is pi square to 30 square is 30 over 2 square is 4 divided by 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the area of the green semicircle equals to 30 pi over 4 times 2. Here we have 30 over 2 is 15. So in total, the value of this expression equals to 15 pi over 4. And 15 over 4 is 3.75, so in total the value of this expression is 3.75 pi. Or in terms of numbers, 3.75 pi is 11.78. So in conclusion, we actually found out that in both methods, the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Okay? Thank you very much.